Okay, last time we did finish up the chapter 12, which was bonding. I did put out an announcement. Again, we're gonna have a quiz on Wednesday for chapter 12, so the bonding. We'll do that obviously at the beginning of the lecture, and then we'll cover all of that chapter. So anything involving bonding, we'll be on it. We're now gonna go backwards here and head back down to chapter 5, I think is this one here. And we're going to talk about nomenclature and how to name everything. So, nomenclature is, again, a fancy way of just explaining how to name things. And it really does revolve around the bonding chapter that we just talked about, which is the two different types of bonding that we came across, which again is ionic bonding. And really, with ionic bonding, as we talked about, it's always a metal, metal and non-metal. And remember, again, as we talked about in that bonding chapter, that when we do get these combinations together, because of their periodic trends, we are going to see that transfer of electrons from the metal to the non-metal. That's going to create our cation from our metal, which is positively charged. That'll create our anion from our non-metal, which is negatively charged. And once again, it is that opposite attraction there that holds that together. We have no sharing of electrons. And that's different than the other type of bonding that we talked about, which was covalent bonding. And covalent bonding, again, is between two nonmetals. And because of those periodic trends, they both basically have all the characteristics that they want to basically hang on to their electrons. They want to bring electrons towards themselves. So the best that they can do, as we talked about, is sharing those electrons. And remember, as we talked about in the bonding chapter, the sharing of electrons may be equal sharing, which is known as a nonpolar bond, may be unequal sharing, which is known obviously as a polar covalent bond. But there is some aspect of sharing that happens there in covalent bonding. And covalent bonding are sometimes referred to as molecular compounds. And these differences here in terms of really the types of bonds that we have in a particular compound also determines really how we go about naming a particular compound. So it does play a pretty good role in terms of naming, whether or not you got sort of an ionic bond happening or you have a covalent bond or molecular bond sort of happening. Now, also something that we saw, I think, in a previous chapter, really important for naming is the charges that certain things make on the periodic table. So a reminder that things in group 1 will make a +1 charge. Things in group 2 will make a +2 charge. Skipping over here to group 3, that's really aluminum there, will make a +3 charge. We do skip group 4, and then at group 5, our nonmetals -3. Again, we got kind of that staircase coming down. Group 6 -2, and group 7, thank you, -1 coming down this way. So we have the +1, +2, +3 in the metal region, and that is where they will lose electrons and become positive. As we get to the upper right, starting group 5, nonmetals that gain electrons, -3, -2, -1. A reminder again that things really do not have charges unless they are kind of hooked up, metal and non-metal together. When they are by themselves, they really don't have charges. Now in the transition metal region here, we do have a variable positive charge for everybody. Also, just to the right, kind of in this location, things like lead, tin, and antimony, bismuth, although they are technically not transition metals, they do have the ability to make a variable positive charge. So it does depend on the situation as to what charge they may make. There is 3 exceptions for the transition metal region that, although they are transition metals, they actually do have fixed charges. And those 3 are right next to each other. We have zinc and cadmium, which both basically make a +2 charge. If you hang a left there at cadmium, you will run into silver, and silver will always make a +1 charge. So those 3 elements, although they are transition metals, are essentially sort of exceptions to variable charge. They have fixed charge along the way. One of the main things that we will talk about is whether or not the metal has a fixed positive charge or a variable positive charge. That plays a really big role in terms of how you go about naming things. And as we will also talk about, pretty much it's the metal that is the most important thing, really. Whenever you got a metal involved, it's really, again, the most important thing. Any questions on that there? All right. So a couple of things. There are a few things that really do go by common names, and probably the big one is H2O. H2O is water. It is not dihydrogen monoxide because nobody wants a refreshing glass of dihydrogen monoxide, right? So they much have a refreshing glass of water. So if you see H2O, you should always call it water. It's not a trick question or anything like that. NH3 is ammonia. It should not be confused with something we'll see a little later on in this chapter, which is some polyatomic ion, which looks very similar, but it has an extra hydrogen and an extra plus charge, and that's ammonium, NH4 plus. CH4 is the simplest organic molecule you could have, stuff that comes out of the Bunsen burner there when you light it, some methane. And so if you see any of those three, they really should kind of go by common name. So as I mentioned before, there's two types of compounds we're going to really talk about. Ones that contain basically a metal and a nonmetal, and ones that contain two nonmetals. Again, our difference here in terms of bonding, ionic versus covalent and sharing of electrons rather than a transfer of electrons. Now, when we name a binary ionic compound, which is always going to be a metal and a non-metal, there are a couple of rules that we follow, and a couple of those we touched upon earlier on in the end of one of those chapters. I think it was chapter 4. But the idea here is we always go with the positive guy first. So when we have an ionic compound, which is what you always get with a metal and a non-metal, the cation should always be named first. It should also come first in the formula. And the anion or the negatively charged guy should always come second. So it's always positive and second. So again, if we had a sodium ion and a chloride ion, when we would write the formula, it would end up as NaCl. Positive guy first, cation, followed by the anion that is there. Another really important thing that we touched upon in that previous sort of chapter at the end was the idea that whenever we put together something that is a positively charged ion with a negatively charged ion, when you put it together to write the formula, it should always equal 0. So in this case, we have a +1 charge and a -1 charge. So when we put it together in an ionic compound formula, no charge. So there should be no charge in that formula. So when we do write a formula for an ionic compound, it has no charge, but it actually is made up of two things that do have charges. It is made up in this example here of a sodium with a +1 charge, which is, by the way, our cation, right? And a Cl minus here, which would be our anion. So the reason we want it to equal 0 when we put together the positively charged ion and the negatively charged ion is actually for what we talked about a couple of chapters ago. That's the electron configuration and also the bonding here. And that is when we do this, each of those guys will achieve that noble gas configuration in terms of their electrons. So if you remember, that's the really stable sort of configuration. And but when you put that positive guy and negative guy together in the simplest way possible to get a 0 charge, that will essentially give you everybody reaching that noble gas configuration and a really stable bond. So as you can look on the periodic table, sodium with a +1 charge, because it's group number 1, when it loses 1 electron, it ends up with 10 electrons, and it backs up to neon's configuration, which again is a noble gas by losing that 1 electron. If you look on the periodic table for chlorine, that's 17. It has 17 electrons. When it gains one charge, one electron becomes negatively one charge. It moves forward on the periodic table to argon, which is number 18 in terms of its electron configuration. So again, the idea there is what we were talking about earlier in those chapters. The goal of all bonding is to achieve that noble gas configuration. And again, a reminder, when a metal and a non-metal get together, the way it's able to do that is metals will lose electrons and go backwards on the periodic table to the noble gas that comes before them. Non-metals will gain the electrons, go forward on the periodic table to the noble gas that comes after them. And again, that creates a really good bond that happens. Now, when we do have ions, which are things that have charges, there are a couple of things that we want to keep in mind if we have to write a formula. So if you had to write a formula for a cation, which again is a positively charged ion, if it's anything that is positively charged, frankly, we just use the whole name of the element. So sodium with a +1 charge would be known as the sodium ion. H plus would be known as the hydrogen ion. Again, just using the whole name of the element. Ca2 plus will be our calcium ion. So a cation in general, if you do have to write the formula for a cation, it should always include the charge because it has a charge and it's by itself. And you just basically use the whole name of the element. Now, when we get to the anions, it's a little bit different. When we get to the anions, which are negatively charged ions, we actually do use the root of the name, kind of the basis of the name for the metal or the element. I'm sorry, for the element. And we replace the last part of the name with IDE. And sometimes it's a little bit more than the last part, but some of the last part there. So if I had Br minus, I had H minus, which hydrogen is one of the only elements that can go both ways. It can be positive in certain cases, can also be negative in certain cases as well. So if you see a hydrogen that comes after a metal, it's going to be the negative version of it. Most of the time it's going to be the positive version, but hydrogen can go both ways. If we had something like O2 minus. So Br is bromine, but with a -1 charge, we drop the last part of bromine, and this becomes the bromide ion, IDE. Hydrogen, obviously, there is the name for that element. It has a negative charge, so we drop some of the last part of the name, replace it with IDE, and becomes the hydride ion. Oxygen, obviously, is the element name for O, and we drop a lot more than the last part of the name there, but it becomes the oxide ion. So, negatively charged guys, same deal. If you have to write the formula for an anion, you're going to make sure it has a charge. You also will, again, take the base of the name there, kind of lose the last part, add the IDE. Any questions on that there? Now, when we talk about type 1 and type 2 compounds, first off, these are both always a metal and a non-metal together. And by the way, as we talked about many times, whenever you have that combination, it should automatically ring the bell of we are dealing with an ionic bond, because that, again, is the only situation where you're going to have a metal and a non-metal together. Now, whenever, as I mentioned a second ago, whenever you're dealing with naming, it is always the metal that is going to determine how you name it. So if you have a metal involved in a compound and you want to name it, that is usually really the most important thing, is that metal. And there's going to come across basically two types of metals. You're going to come across ones that are sometimes referred to as a type 1 metal or a type 1 compound. It's an ionic compound. A type 1 metal has a fixed positive charge. So again, if you go back to the periodic table, as we just talked about a second ago, the metals on the periodic table that have a fixed positive charge are the metals in group 1, group 2, group 3, which is aluminum, and those three transition metals, zinc, cadmium, are silver. So if you see a compound that contains a metal that falls in any of those places on the periodic table, automatically you know it's a type 1 compound. Automatically you know it has a fixed positive charge. And it kind of makes the naming a lot easier. You just kind of roll right into the naming, as we'll talk about in just a second. So that is what you want to look for. Now, if you look at the metal and it does not fall in one of those places on the periodic table, it is not part of group 1, it's not part of group 2, it's not part of group 3, and it's not zinc, cadmium, or silver, it most likely is going to be a type 2 metal. And a type 2 metal, the difference is it has a variable positive charge. And those are, in most cases, your transition metals are just to the right under the staircase. Again, where we see things like lead, tin, etc., and that sort of location, kind of underneath that staircase, which are metals. Again, because these have a variable positive charge, it has an effect on the way that we name these guys, because in certain cases, we could be talking about, for example, there, the chromium with a +2 charge, but in other cases, that chromium could have a +3 charge. Or something like copper. In certain cases, copper may have a +1 charge, and in other cases, it may have a +2 charge. So we do need to do slightly different thing when we name those guys. But again, it's the metal you always want to look at. So that should be really, when you kind of go through naming, you want to kind of go through a couple of steps along the way. The first step I would recommend is determining what you're dealing with. And what I mean by that is, are you dealing with a metal and a non-metal? Are you dealing with two non-metals? Once you see you're dealing, for example, in this case, with a metal and a non-metal, you know it's an ionic sort of compound. It's an ionic bond. You have cations and anions. You got ions that are present. The next thing you want to do is, once you see that metal, you want to determine where it is on the periodic table. And based on where it is on the periodic table, that's going to allow you to properly sort of name it. Any questions on that there? So here's a table from your book of just simple ion names. And you can see all these guys over here are positive. We're just using the whole name. On our negative side here, everybody is getting the IDE treatment there at the end of the name. And once again, as I mentioned before, hydrogen is really the only element to kind of go both ways, positive or negative. And once again, you only really see, for example, hydrogen in the negative when it comes after a metal. So if you had something like this, LiH, this is lithium with a +1 charge, and the hydrogen here would have a -1 charge in that case because a metal's involved. So that is sort of when hydrogen can become negatively charged. All right, so let's talk about the rules for naming type 1 compounds. So once again, type 1 ionic compound, it's ionic, which means, again, metal and non-metal. That should be a no-brainer at this point. That is what we're dealing with. Once again, it is the metal here that's going to make it a type 1, and it is what we want to look at. So again, that metal, as I just mentioned a second ago, will be from group 1, 2, 3 on the periodic table, zinc, cadmium, or silver. And the nice thing about naming these guys is this: as soon as you identify that metal as being a type 1 metal, there's absolutely positively nothing else that you need to do to figure out the name. So as soon as you identify it, that's a type 1 compound. You could roll right into the name. You don't have to figure out charges, balancing anything, just simply lay out the name. How do we name these? Very simple. We take the whole name of the metal, and our non-metal, we drop the last part and those guys get the IDE. So we just take the whole name of the metal, second guy, we get the IDE treatment. So that is why when we take something like NaCl, for example, if we were going to go through this to name it, the first thing you want to identify is what you're dealing with. Na is a metal, Cl is a nonmetal. That should check the ionic box always. Once you see a metal involved, that 100% of the time is the most important thing to look at. And when I go to the periodic table, I can see sodium is in group number 1. So that is group 1. That means it has a fixed positive charge, and that makes it a type 1 metal. And that basically is all the information I need at this point. I could just roll with my code here. Whole name of the metal, so the metal is sodium. The non-metal, we're going to drop the last part of the name, and that's going to be IDE. And we're going to go from chlorine to chloride. So this will be sodium chloride, yeah? Will be our name here. Again, there's nothing else to figure out. There's nothing else to worry about in this particular case. Any questions on that there? Now, a reminder that when we do look at a formula, as we mentioned before, the formula for an ionic compound always will have no charge. But again, it's important to remember that it is made up of things that do have charges. So once again, if we take a look at this, Ki, K is potassium, which is a metal. I is a nonmetal. So once again, that should check the ionic box. Looking at the metal, once again, we see potassium in group number 1 on the periodic table. So that is group 1, which means it has a fixed positive charge. It's a type 1 metal. So at that point, we could just roll into our name. Again, whole name of our metal, potassium, and iodine becomes iodide, IDE, and this is potassium iodide. Once again, although the formula here of Ki has no charge, it is made up of a cation that is positively charged, which is K plus. It is made up of an anion which is negatively charged, which is Cl minus, as that is group number 7. And once again, the reason we only have one of each of them in this formula, +1 and -1 when we put it together, gives us a 0 charge. So we only need one of them for each of those cases. Questions on that there? Same thing if I looked at CaCl2, for example. This is calcium, which is a metal. This is Cl, which is a nonmetal. And once again, that combination is going to check the ionic box. We're going to focus our attention on the metal. The metal here is calcium, which is group number 2. That means it has a positive 2 charge and a fixed charge. So since that is a group 2 metal, again, it has a fixed positive charge, makes it a type 1 metal. That is all we need for this. That is going to be calcium, whole name of the metal, and chloride here for our nonmetal. So this is calcium chloride in this case. And one of the things that's really important is this is calcium chloride. This is not calcium dichloride. There is no prefix in this guy. People always want to make a calcium dichloride because they're like, hey, isn't there 2 of these? And the answer is, yeah, there is 2 of them. Has no effect on the name. You could have like 400 of them. It will still be called chloride at the end. The reason we have the 2 there is what we talked about with bonding and everything else, right? We have calcium that has 2 valence electrons. We have chlorine, which is group number 7, has 7 valence electrons. When calcium gives away its 1 electron, That's not enough for calcium to achieve noble gas configuration because that will only move it back to potassium, as we talked about, right? It actually needs to give away 2 electrons. Chlorine here cannot accept anymore, so we don't just have one chlorine, but we have the second one, right, to accept that second electron. That again is going to give us the calcium that now has a +2 charge, and we have not one, but 2 chloride ions. And that is what the 2 represents. The 2 on the bottom represents that you have 2Cl minuses. It does not, by the way, represent that you have Cl2 minus. No such thing, yes? So you have 2Cl minuses individually here. And that, again, is what we have there. Once again, it has absolutely no effect on the name. So using prefixes in the wrong locations is a very common error that a lot of people make. So here's an easy way to remember it. If you have a metal in your compound, you should not be using prefixes unless you're like an X, yes? So anytime you have a metal and you're naming something, you pretty much should never have a prefix in that name. It should not belong there with a metal. So no prefixes with metals. That's an easy way to remember it. There's only like a couple instances where it could happen, and we'll talk about it, but the general rule is if you have a metal, pretty much 100% of the time, there will be no prefix in the compound name, and you should not use it. Any questions on that? By the way, as well, if I had multiple metals, it will not affect the name either. So if I had multiple calciums, it would just still be calcium. So we, again, do not use prefixes anywhere near a metal. And that's, again, a very good way to remember not to do it in the wrong situation. Any questions on that? All right, so why don't you take a few moments here for each of these, give the proper name. Why don't you also give the formulas for these guys here? So let's go with sodium oxide. Let's do aluminum sulfide. Let's do let's go with magnesium chloride. All right, so let's do names on the left here and formulas on the right. So take a few moments there to see what you come up with. Okay, let's take a look here. So, once again, as I mentioned before, good sort of process when you're naming something is to identify what you're dealing with first. So, hopefully, you can recognize potassium there as a metal, Cl is a nonmetal. So, again, that should tip you to ionic as you have a metal and a nonmetal together. Once again, when the metal is involved, it is the most important. And again, we look at K, which is group number 1 on the periodic table. And because it's group number 1, it has a fixed positive charge. And that tells us this is a type 1 compound because of that metal that's involved. And at that point, that's all we need to name it. We're just going to go whole name here of the metal, which is potassium. And the non-metal is going to get the IDE treatment. So this would be potassium chloride in this case. A reminder here that the cation is K plus, is our cation. And our anion is Cl minus, group number 7 on the periodic table. And that, once again, is why we only need one of each when we put it together. +1 and -1 gives us no charge when we put the formula together. Any questions on that one there? Once again, looking at the next one, zinc is a metal, sulfur is a nonmetal. So once again, that should check the ionic box. Metal is all where my focus is going to be. I do see that this metal is a transition metal, but it is one of those ones with a fixed positive charge. The zinc, cadmium hang a left there to silver. So because it is a fixed positive charge, it is a type 1 metal. And that, again, is all we need. We're going to go with zinc, the whole name of the metal, and sulfide from sulfur, IDE at the end of it. Once again, our cation in this case is zinc with a +2 charge, which is its fixed positive charge. And the sulfur, which is group 6, will have a -2 charge. That is our anion. And once again here, that is why when we put it together, we just need one of each. +2 and -2 gives us 0 when we put it together. Taking a look at the next one, we got calcium and bromine. So that is a metal nonmetal. So once again, it's ionic. Taking a look at my metal there, calcium's in group number 2 on the periodic table. Once again, tells me it is a fixed positive charge, +2. That checks the ionic box. That is all I need for the name. Whole name here, calcium for the metal. And once again, our nonmetal gets the IDE. And once again, as we talked about, the 2 here has no need or effect on the name, so no prefix. Once again, to remember that, metal involved here, so no prefix for sure. The cation here is calcium with a +2 charge. And a reminder that the anion here is Br- from group number 7. That is our anion. It is not, again, Br2 on the bottom and minus on the top there. So there's no such thing as that. So again, the 2 means we have not one of those Brs, but we have 2 of those Br minuses, and that is the proper formula there for our anion. Any questions on that one there? Next, we have barium, which is a metal. Hydrogen is actually a nonmetal, so this is going to be ionic. In this case, barium is also group number 2, which means it's a type 1 fixed positive charge. And now we could roll to our naming, which is barium. And this is actually the negative version of hydrogen, and this will be hydride, IDE here. Our cation in this case is barium with a +2 charge. And our anion is actually H with a -1 charge. Once again, no prefix here. The 2 there just indicates we have not one, but we actually have 2 of those guys basically present to balance out the charge. Any questions on any of those names there? Say again? It's one of those exceptions in the transition metal, and that is the positive charge that it always makes. So it has a fixed +2 charge. And same with cadmium right below it. And then that has a +2 charge. You hang a left to silver, has a +1 charge. So it's like a kind of like a backwards L right there, those guys. The zinc, cadmium, and then silver. And these guys +2. Good way to remember that is zinc and cadmium are 2 elements, right? So +2. Over there to our 1 element of silver +1. And again, those are 3 exceptions in the transition metal region that although they're transition metals, they will always make a fixed positive charge. So they're named as type 1 compounds because of that. Other questions? Now, when we go to name, write the formula from a name, we still want to identify what we got going on. So sodium is a metal, and oxide is oxygen, which is a nonmetal. So what that tells us is we are dealing with an ionic compound. And when we're dealing with an ionic compound, that means we're dealing with ions. And whenever you want to write the formula for an ionic compound, you simply want to put the ions together in the simplest way possible to get to 0. So what we want to start here with is what are the 2 ions? So sodium is group number 1, which means the sodium ion has a +1 charge. Oxide is oxygen, which is group number 6 on the periodic table. That means it has a -2 charge. Once again, when we put these together, we need to equal 0. So hopefully you can see you need more of the positive guy there to get to 0. So you actually need not 1 sodium ion, but you need 2 of them. That's going to get you a grand total of +2 to balance out that -2 that's happening there. And basically at this point, we could put together exactly what we just wrote. I have 1 and 2 sodium, so the 2 on the bottom, the 2 always goes to the guy to the left. And I only have 1 oxygen, so just put an O there for the 1. And that will give me Na2O as the proper formula here. Any questions on that there? Taking a look at the next one, that's aluminum and sulfide. So aluminum a metal, sulfur a non-metal. So once again, ionic. Aluminum is group number 3 on the periodic table, means it has a positive 3 charge. Sulfur is group number 6 on the periodic table, has a -2 charge. So once again, when we put this together, we need to equal 0. If you're not sure what the common number is, just multiply the two numbers together. 3 and 2 is 6. So to get my aluminum to 6, I need not 1, but 2 aluminum ions. And to get my sulfur to 6, I need not 1, not 2, but I need 3 of those sulfide ions. That's going to net me a -6 over here to balance out my +6 over here. And at this point, I could just write my formula. I have 2 aluminum, so that's an aluminum with a 2. I have 1, 2, 3 sulfurs, which is right there. And now we have our correct formula in this case. Any questions on that there? Lastly, here we have magnesium chloride. Magnesium is a metal. Chlorine is a nonmetal. So once again, ionic and ions. Magnesium is group number 2 on the periodic table, number 12. That means it has a positive 2 charge. Chloride is group number 7 on the periodic table, has a -1 charge. So once again, when we put this together, we need to equal 0. You hopefully can see that you actually need more of the negative there. You actually need one more of them. That gives you a grand total of -2 to balance out the positive 2. And that is MgCl2 in this case when you put it together. And you will have the proper formulas. First off, any questions on any of those formulas or anything like that there? Correct. Uh, it's -1 because essentially everybody in group number 7, its electron configuration will end in like P5, yeah, and the P subshell could hold 6, so they have room to gain 1 electron, right? And they will each gain 1 electron, and that's why they become -1 charge. If you back up one to like oxygen, which is group 6, if you did like the electron configuration for everybody in that group, it would end up at like 2p4, and that means they could hold 2 more electrons or gain 2 more electrons, and that's why they typically will end up with a -2 charge. Right. Exactly, because it has this room in those p subshells to gain those 2 electrons. Yeah, so that's why those guys end up with those fixed charges. It's like we were just talking about. If you just look on the periodic table, those guys are non-metal, so they're going to go forward when they gain electrons to the noble gas. So what for group 7, basically they need 1 electron to get up forward. Group 6 needs 2, and then group 5 there needs 3 to get forward for our non-metals to get to that noble gas of 8. Yep, yep, yeah, yeah. Other questions? All right, a couple of things in terms of type 1 naming before we kind of move on was um, this, I think, maybe. Now, I'm going to talk about it here because it sort of goes here, and that is let's talk a little about hydrogen. Now, hydrogen really is, and H plus specifically, it really is a non-metal, right? Which is hydrogen. But hydrogen, as you can see on the periodic table, is hanging out over there in group number 1. And it does have some unusual sort of properties, one of which, as we just saw, it can be positive or negative, so it can kind of go both ways. So, although hydrogen is a nonmetal, and when it hooks up with another nonmetal, like, say, chlorine, we do tend to think of this more like an ionic compound than really what's happening, which is, as we know from Lewis structures, they're sharing electrons, right? So it's really covalently bonded. But because hydrogen has a lot of properties, especially when something like this goes for a swim in water, it will actually make an acid and will then become ionized, and there will be some ions that will be formed. In terms of naming things with hydrogen, we typically will kind of treat it like a type 1 metal, even though, in terms of naming, even though, again, it is a non-metal and is sharing electrons. So if this was a gas, for example, this would be called, same rule, hydrogen chloride. So we would call this hydrogen chloride. So sort of an exception is we really don't name hydrogen as like a non-metal sort of interaction. We kind of name it very much like group 1 or type 1 sort of compounds. Even if you had multiple hydrogens like this is thought of as being hydrogen sulfide gas. And we think of this like there are two hydrogens with plus ones and a sulfur or sulfide with a -2 charge. So it's not correct in all aspects because definitely there's sharing of electrons here. But because this, in a lot of cases, are the root of acids, which when they do go in water and you do have an acidic solution, do make ions, they are named very much like a type 1 sort of compound, even though, again, hydrogen is a nonmetal. So that's a slight exception, which is hydrogen. If you have it like this, you could think of it as like H plus and whatever the negative guy is, and you just name it like a type 1 sort of compound. Any questions on that? Now, the other thing that sometimes people are taught is this, which is, you know, you have aluminum and you have oxygen, and you want the formula, just bring those things down, and you end up with Al2O3. Or if you have a formula like this, and you want the ions, just bring these things up this way, and you will end up with calcium with a +2 and bromide with a -1. And the truth is, it does work about 93% of the time. It does not work 100% of the time. So if you're just blindly switching things, you will come across a lot of things that you will end up with the wrong answer. But I'll be honest with you, a lot of people are taught this way, and it does work. And like I said, probably like 93, 94% of the time. But again, you should think about balancing out to zero like we've been talking about, and that's probably the best way. You'll always get the right answer. But again, if you just kind of blindly just kind of go up and down with those things, you will come across several that will not work right for you. So just keep that in mind if you happen to see that somewhere along the way. Any questions on that? Okay. All right. Let's then talk about type 2 ionic compounds and the difference between them. Type 2 compounds, again, are still ionic. So we are still dealing with our metal and nonmetal. And because we are still dealing with a metal and nonmetal, and because a metal is involved, once again, the metal is the most important thing to look at. This is going to be our transition metals, are just to the right under that staircase. Now, what these guys have in common, as we talked about, is they have a variable positive charge. So they do not have a fixed positive charge. So for example, in some cases, copper, as we saw there, could be +1. In other cases, it could be +2. Again, any of those guys there, nickel could be +2, could be +4. So because it does have a variable charge, we do have to kind of approach it slightly different. So if we start with something like the example there, which is FeCl2, we would take our same approach here in terms of naming, and we would go with iron, which is a metal, Cl, which is chlorine, which is a nonmetal. So that checks the ionic box. Once again, looking at the iron, we will see that it is a transition metal, which means it can have a variable charge. So when we see that, that tells us it's a type 2 compound. And because it's a type 2 compound, we do have to do a slightly different thing when we name these. And it is named similar to type 1, which is we're still going to use the whole name of the metal or the positive guy. We're still going to go non-metal is going to get the IDE at the end. The additional thing that we put into these is a Roman numeral. So we do use a Roman numeral. And it's really important to understand what the Roman numeral means. And people always screw this up. They sometimes think that the Roman numeral means how many metals there are, and that is not what it means. The Roman numeral is the positive charge on one of the metals ions. So if you just took out one of the metal ions, or the cation, what is that positive charge? And that is what the Roman numeral means. So how do you know what is the positive charge on the metal? The good news is whenever you come across this situation with a metal that is a type 2 metal, you will 100% of the time always know the charge on whatever it is attached to. So whatever it's attached to, you will definitely know what the charge is. So how's that work in this situation? Well, I know iron is a type 2, so at this point, I'm not sure what the charge is because it could be a variable positive charge. But I for sure know when I look at Cl, Cl is group number 7 on the periodic table, and that means that Cl should have a -1 charge. And I know that I do not have just one of those Cl's, but I have two of them, and that gives me a grand total of -2 for my Cl's. I know that this is an ionic compound, which means the overall charge of this formula should be 0. So if my negative guys are -2, that means my one iron, to balance it out to 0, would have to have a +2 charge in this case. And that is the one additional step you have to do in these type of compounds, is you need to figure out what is the charge on the metal. And once you do, you're ready to name it. And this name would be iron, Roman numeral 2. And once again, the 2 is for the charge, not how many we have. And just like in type 1, no prefixes here because a metal's involved, and it doesn't matter that there are two of the Cl's, it is still just going to be called chloride. And this would be iron Roman numeral 2 chloride in this case. Any questions on the name? Now, why do we need the Roman numeral? The reason we need the Roman numeral is because of that metal. So let's just say I had FeCl3 in this case. Same deal, we have a metal, non-metal, ionic. Same deal, iron's a transition metal, which means it could have a variable charge. I need to figure out the charge on the iron in this case. And just like above, I have just one iron. I do have Cl, which is still group 7. There's not one, but there's 3 of them. That gives me a grand total of -3 in this case for the Cl's. That means the iron in this case is not +2. It needs to be +3 in this case to balance it out. And the name of this guy would be iron Roman numeral 3. Once again, chloride in this case, as our +3 charge is what the Roman numeral means. So naming is all about telling the person, like in the first one, I'm talking about the iron with the +2 charge. In the second one, I'm talking about the iron with the +3 charge. So you have to kind of tell the person that is what's happening in this case, and that is what the Roman numerals are for. That is also why we do not need Roman numerals for type 1 metals, because sodium can only be +1. There's no other charge that sodium can have. So because it has a fixed charge, you don't have to tell people, hey, this is sodium with a +1 charge, because it can never be anything other than that. So that is why we do not use Roman numerals there in the type 1 compounds. Question on that there. It, it is all transition metals, and uh, underneath the staircase where like lead, tin, antimony, bismuth, and that sort of general area, which are not transition metals, they also can have a variable charge. Like something like lead, which is Pb, could be like +2, +4. So something like tin, same deal, +2, +4. So although they're technically not transition metals, just a little bit to the right, and it would be underneath the staircase because that's where metals would be. Um, they can also, they're named the same way because they have those variable charges. Yeah. You know because the only three exceptions for transition metals that have fixed charges are those three: zinc, cadmium, and silver. They have fixed charges. That's why they're named as type one. Anything else that falls in the transition metal region or just to the right of it, you could safely assume it's going to be a type 2 metal and can have a variable charge. And the way you figure it out is what we just did here. You will always know whatever it's attached to, what the charge of it is, and you have to kind of back calculate what the positive charge would be for the metal, knowing the fact that it has to equal zero overall when you put them together, right? And that's how you would figure out what the actual charge is. So the only thing you have to remember is if it's zinc, cadmium, or silver, those guys fixed, and they're type 1, no Roman numeral needed. Everybody else, Roman numeral needed. Yeah. Other questions? What's that? Yeah, so the three exceptions for type 2 are which are type 1 guys is zinc and cadmium. They're always plus 2. And if you hang a left there to silver, it's always plus 1. So these are not considered type 2 because they have fixed charges. And everybody else, though, in that region will be considered a type 2 metal. And just to the right as well, and will need a Roman numeral. Yes, they were type 2. So you would have to, it depends on what they're attached to. So you don't know what the charge is until you see it in a formula because it depends on what it's attached to as to what its charge would be. Just like we see here, right? In the first one, the iron is plus 2 because it's attached to 2 Cls. And the second one, iron is actually plus 3 because it's attached to 3 Cls. I don't know what iron will be unless I see it in a compound what's attached to. That's how you figure out what the actual charge is by working backwards by what it's attached to. Iron's two common charges is plus 2 and plus 3. And those are the two common ones that pop up most of the time. Same thing with like copper. Copper in a lot of cases can be plus 1, and its other very common charge is plus 2. Again, it depends on what it's attached to as to, in that situation, what the charge is. And that is really the whole purpose of the Roman numerals to tell people, hey, in the first one, we're talking about the iron that has a plus 2 charge. That's why it has a Roman numeral 2. In the second one, we're talking about the iron with a plus 3 charge. That's why it has a Roman numeral 3. Not usually. So a lot of things in transition metals have common charges that they do make. Not one charge, but they have multiple like common ones that very much pop up. Transition metals can make a lot of different sort of what are sometimes referred to as oxidation states or charges, but they do have very common ones. And the common ones for transition metals are usually, in a lot of cases, plus 2s, plus 3s, occasionally plus 4s. Those are the common ones that you most often come across. But there are some things like, for example, Mn can have different oxidation states of like I'll wear it to like plus 8, plus 6, a kind of weird different charge. It has the ability to do that. Not commonly found in like those high sort of charges. So I would say most things plus 2s, plus 3s, plus 4s are plus 1s are very common sort of charges that you see. But there are certain ones that can have some weird sort of numbers. And it, again, just goes back to what it's attached to. It kind of determines that. Other questions? All right, so why don't you take a moment here and decide what should the proper name be for this one? PB is lead. Okay, so once again, we want to identify what we're dealing with. So PB, once again, is a metal. O is a non-metal. So once again, that does tell us it's ionic. Whenever a metal is involved, that is the most important thing. And this metal is found, if you look on the periodic table, just to the right of the transition metals there underneath the staircase. So as we were just talking about, this does fall under a type 2 metal because it can have a variable charge because of its location. So we need to figure out what the charge is. We do have one lead. The good news is, as I mentioned, you will always know what the charge is of whatever it's attached to. Oxygen is group number 6 on the periodic table, which means oxygen should have a -2 charge. Once again, there's not one of those, but there are two of them. And if you put that together, that gives you a -4. That comes together here to 0, means that the lead needs a +4 charge. And this would give you lead Roman numeral 4 because of the charge. Oxide. This would be one of those ones that I mentioned a second ago that if you just don't think about it and you just like, oh yeah, I just move it that way and that way, probably some of you might have lead 2 on your paper and you would be wrong. So again, the little switcheroo thing does not always lead you to the right answer. You would also think, if you weren't really sure, that oxygen would have a -1 charge, which is also wrong as well if you flipped it that way. So again, a reminder, if you can try the flipper thing, it does work 93, 94% of the time. You will not get them all correct in this case. Any questions on that there? Now, there is an older way of naming these that we are not going to use for type 2. We will strictly use Roman numerals, but it does pop up occasionally. And that is, instead of using Roman numerals, people will use sort of the historical sort of name for the element. And they will end it in either ic, which usually is the one with the larger positive charge, or the ous, for the one with the smaller positive charge. And so, for example, iron 3 versus iron 2. Iron 3 has a larger positive charge, so sometimes people call that the ferric ion. And iron 2 has a smaller positive charge of the 2. That's sometimes referred to as the ferrous ion. Same thing with copper. Copper 1 would be the cuprous ion. Copper 2 would be the cupric ion. I would say copper and iron are sometimes in papers and stuff still referred to that way as ferrous or ferric and stuff like that. But for us, we will not use that old name way of naming. We will strictly stick with Roman numerals. But in case you come across something like that, weird name, it's basically probably the older name, and the ending tells you whether or not sort of the larger positive charge or the smaller positive charge in that particular case. And here's an example of a table from your book of that. And again, we won't really use this older name. You are responsible for the Roman numeral name. One other sort of weird thing that occurs with type 2, and one that confuses people a lot, is mercury. Mercury is a type 2 compound. There could be mercury 1 and mercury 2, which is Hg. Now, Hg 2 plus and a 2 on the bottom with all those 2's, oddly, is mercury Roman numeral 1. So the one with all the 2's is actually mercury 1. And mercury like this with just the 2 up on top with the charge is mercury 2. The reason there's a 2 on the bottom is mercury 1 comes as what's known as a dimer. It is 2 mercury 1s hooked together. So that is where the 2 comes from, because there's 2 of them on the bottom there hooked together, and the +2 charge is because each one is a +1 charge, and that's how we get to this guy up here on top. How do you know which one it is based on the formula? The bottom 2 hangs around. So when you look at a formula of this, Hg2O versus HgO, the one up here, that is the 2, that is this 2, and that is actually mercury 1 oxide. This guy does not have the 2 on the bottom, and that is mercury 2 oxide, the bottom one. So that is the 1 version of mercury. That is the 2 version. So that 2 on the bottom does tend to hang around when you put it together with other elements in a sort of formula, and that's a good way to recognize, which one it is, mercury 1 or mercury 2. Again, you will not see that bottom 2 obviously there usually, if it is mercury 2 in that particular case. Any questions on that there? All right. So as I mentioned before, we basically want to Use a Roman numeral. Once again, that is to indicate the charge on the metal. So to finish up here, let's take a look at each of these. Let's do names on the left and